Okay, let's start do a network session. First part is by two-way me and Matus Logistic, the implicit bias operating descent on non-separable data.
Thanks for the introduction. This is joint work with Matus Logistic. Here is an outline of the talk. I will first give the problem description and theorem statement. Next, I will give some visual illustration of our results. Okay, sorry. Okay. And finally, I will briefly discuss proof ideas. So let me describe the problem first. We consider the binary classification logistic regression model with training examples in RD and labels -1 or +1. They are collected into an n by d data matrix A whose ith row is equal to xi, yi. In this work, we actually only consider linear classifiers, but some of the proof ideas can be extended to deep linear networks, and they might also be useful when analyzing nonlinear networks. The empirical risk is defined as usual with the exponential loss or the logistic loss. We use gradient descent to minimize this empirical risk on the unbounded domain RD without regularization. Here is our main theorem. We prove that for an arbitrary dataset A, it can be uniquely decomposed into first, a strongly convex part AS, meaning that the empirical risk for this part is strongly convex, and second, a separable part AC. And moreover, if we run gradient descent with step sizes 1/√T on the whole dataset A, then actually the gradient descent iterates can simultaneously satisfy the following two conditions. For the strongly convex part AS, it converges to the unique optimum at rate 1/√T. On the other hand, for the separable part AC, it can maximize the margin at rate 1/log_T, subject to the condition that it converges to the unique optimum for the strongly convex part. Actually, this last condition is the tricky part, and it actually causes the main difficulty in the proof. So if actually the strongly convex part and linearly separable part are orthogonal to each other, or in other words, if they're independent, then we can actually give a clean analysis for margin maximization. However, in general, they are not orthogonal. There's dependency between them, and with this dependency, this margin maximization problem has a very different structure. We need to handle it in a very subtle way in our proof. Okay, so this is our main theorem. Next, let me give some visual illustration. So in these graphs, blue points represent positive examples, while red points represent negative examples. The squares represent the gradient descent path. So in these examples, the empirical risk is strongly convex with a unique optimum. If we run gradient descent, it will converge to this unique optimum. We can see that as we move the positive and negative examples away from each other, the unique optimum moves along the negative x direction. And if we actually make the data set linearly separable, then the optimal solution will go off to the infinity. And because as we move along this -x direction, the empirical risk will decrease to 0, but this infimum 0 is never attained by any finite linear classifier because the exponential of the logistic loss is strictly positive. And if we run gradient descent on it, it will also go to infinity, minimizing the risk to 0. So now we've seen the strongly convex case and the linearly separable case. It turns out that these two cases are not exhaustive. There still exists a data set which is neither strongly convex nor linearly separable. So what we prove is that, in fact, any data set can be uniquely decomposed into a strongly convex part and a linearly separable part. Here I will just give a very actually oversimplified example. So let's consider this data set. The subdata set which lies on the y-axis gives a strongly convex subproblem with a unique optimum v-bar. The remaining data set in these two circles is linearly separable. We can decrease the empirical risk for this separable part to 0 by taking a linear classifier with a positive margin and extending it to infinity. However, we also need to make sure that we do not increase the risk for the strongly convex part. Therefore, the correct thing to do in this example shown here is to take the linear classifier -1, 0, or denoted by u bar here, and extend it to infinity. In this way, the empirical risk for the linearly separable part will decrease to 0, but we will not change the empirical risk for the strongly convex part. And finally, to minimize the risk for the strongly convex part, we just need to find this optimal solution V bar. So to sum up, this ray here represented by V bar plus R times U bar with R going to infinity, in some sense denotes the optimal solution for this problem. And if we run gradient descent, we can see that it indeed follows this path. So although this example is very oversimplified, actually basically the same thing is true for an arbitrary data set. And in a general case, gradient descent will actually maximize the margin for the linearly separable part AC, while subject to condition that it also converges to the optimum for the strongly convex part. Next, let me very briefly discuss the proof ideas. So for convergence on the strongly convex part, the proof is standard. We first show that the overall empirical risk converges to its infimum, which implies that the empirical risk for the strongly convex part also converges to its infimum, and then we just need to use strong convexity. The tricky part is to prove margin maximization over the linearly separable part. So here, the key potential is this minus log of the risk of WT minus the infimum of the risk. Intuitively, this is some smooth approximation of the unnormalized margin, and we denote it by bar gamma. And we can then use Taylor expansion, and if we ignore second order terms, we can prove that for each gradient descent step, the increase in this unnormalized margin divided by the increase in the length of the linear classifier is at least some factor lambda times the maximum margin gamma. So if the data is linearly separable, the lambda is always 1, and the proof is basically done. But lambda is in general just a factor between 0 and 1. And to deal with the general case, we actually prove that lambda will converge to 1 as the overall empirical risk converges to its infimum. And to do this, we need to handle the dependency, the cross terms between the strongly convex part AS and the linearly separable part AC. Here are some additional comments. If the dataset is linearly separable, then actually similar proof ideas have appeared in the prior work, Logistic 2013. And here in this work, we need to adapt it to handle the dependency between the strongly convex part and linearly separable part. And also, the margin rate given in our paper is tight, and it can be adapted to a rate for the L2 distance between the normalized gradient descent iterate and the maximum margin solution U bar. And to get a rate for this quantity, we need to add another square root. And in another prior work, Saudry et al. 2017, they give a rate, a 1/log rate for the same quantity, which is quadratically faster than ours. However, a clear dependency on n is not given there. Also, the proof techniques in our work and in Saudry et al. 2017 look pretty different, and it is very interesting to understand the trade-off between them. Okay, so here is a summary of our result. We prove that any data set can be uniquely decomposed into a strongly convex part, on which gradient descent converges to the unique optimum, and a separable part on which gradient descent can maximize the margin subject to the previous convergence on the strongly convex part. That's all for my talk. Thanks. And any questions?
Okay, let's thank the speaker again.
Okay. I don't know how to advance this. Do you know how to advance it? Okay. The next speaker is Pedro Savarese, and it's a joint work with Itai Evron, Daniel Sutri, and Nati Cerebro. How do infinite width bounded norm networks look in function space?